Lesson 22, activities. Let's find some derivatives. We're going to speed through these here, so feel free to rewind and slow me down. So what's our notation? dy dx. Okay, derivative of inverse tan is 1 over 1 plus the stuff squared times the derivative of the stuff. So we're copying the stuff here, and then multiplying over here by the derivative of all that stuff, 15x to the 4 minus 14x plus 4. And then the minus 5 disappears. Next one, dy dx equals, okay, inverse sign becomes 1 over the square root of 1 minus the stuff squared. Stuff is the fraction in the parentheses. And then on the outside, times the derivative of the stuff. And that fraction requires a quotient rule. Bottom gets squared. Bottom times the derivative of the top minus the top times the derivative of the bottom. C. ln of stuff becomes 1 over the stuff times the derivative of the stuff. Derivative of cosine is negative sine. Careful, it's not sine. D. This is some stuff to the 10th power. 10 comes down, copy the stuff, subtract 1 from the power, times the derivative of the stuff in the parentheses. Remember, arc sine is synonymous with inverse sine, which we saw today as a derivative of 1 over the square root of 1 minus x squared. E. This one is of the form e to the stuff, and the derivative of e to the stuff is e to the stuff, times the derivative of the stuff. The derivative of inverse tan of x is 1 over 1 plus x squared. F. This is 2 to the stuff. That looks like a to the stuff. So a to the x would be 2 to the x. So this becomes 2 to the stuff, 2 to the ln of x, times the derivative, sorry, I missed something, times ln of 2. That's the a to the x derivative rule. But then times the derivative of the stuff. The derivative of ln of x is 1 over x. And that one's done. Okay, G, arctan of 7x to the 4th times ln of 5x squared minus x. This one is a product rule. First gets copied, times the derivative of the second. ln of stuff is 1 over the stuff, times the derivative of the stuff. That's the first part of the product rule, plus the second, the ln gets copied, times the derivative of the first. Arctan is synonymous with inverse tan, so this is the 1 over 1 plus x squared rule, but it's really 1 over 1 plus the stuff squared, times the derivative of the stuff in the parentheses. Derivative of 7x to the 4 is 28x to the 3. Note that we're not taking the derivative of, oopsies. We're not taking the derivative of 7x to the 4th squared. We're only taking the derivative of the original stuff, which was 7x to the 4th. Okay, H. This is ln of stuff. ln of stuff becomes 1 over the stuff times the derivative of the stuff. And the derivative of this stuff is, again, a quotient rule. We go bottom times derivative of the top minus the top times the derivative of the bottom. So that one looks awfully familiar. So it's exactly the same as one that was up above. No, the one that was up above was inverse sine of the same fraction. So the derivative of the stuff for this part and for part B, the derivative of the stuff, of course, is the same, but then the basic format for the original derivative rule is different. For inverse sine, that's a different rule than for ln. Okay, and then finally I, dy dx equals Okay, this one has lots of nested chain rules, but we can handle it. Starting with the outermost function, that's inverse tan of stuff. Inverse tan of stuff becomes 1 over 1 plus the stuff squared. Stuff in this case is ln of inverse sine of 3x to the 6th. But then times the derivative of the stuff, and now the stuff is starting, no, not there, starting here. So the derivative of that is ln of stuff, which is its own chain rule. So ln of stuff becomes 1 over the stuff times the derivative of the stuff. And now the stuff has changed again. It is this. And the derivative of inverse sine of stuff is 1 over square root of 1 minus the stuff squared. The stuff is now 3x to the 6th, and it gets squared. And then finally times the derivative of the stuff. The stuff is now just the 3x to the 6th, and that is 18x to the 5th. Phew. Okay, in number 2, we're going to create a formula for the derivative of y equals log x by differentiating both sides of that identity. So let's copy that identity, but we'll write some, leave some space in front of both sides. 10 to the log of x for sure is equal to x for every x. And so we're going to take these equals and we're going to take the derivative of both sides and they will still be equal. The right-hand side is easy. That's 1. Left-hand side, 10 to the stuff. That's like a to the stuff. So 10 to the stuff becomes 10 to the stuff times the log of 10, times the ln of 10, times the derivative of the stuff. Give myself more room here. So times the derivative of the stuff, and the stuff in this case is log of x. So we're just putting that in here, and the reason we're putting it is because we don't know what the derivative of log of x is. We might be tempted to say the derivative of log x is just 1 over x, but that was a specific derivative rule for ln of x. This is not ln of x, this is log of x. We don't know the derivative for log of x, but we're about to find it. So the goal here is to solve this equation for d dx of log x. So we are going to divide both sides by all of this, 10 to the log x times ln of 10. So the left-hand side will just be derivative of log x. Right-hand side, 1 divided by everything that we just said, 10 to the log x times ln of 10. And then we're just going to clean this up a little bit. We know, it's underlined in red at the top right, that 10 to the log x equals x. Well, that is right here, 10 to the log x. So that is simply x. So we're going to write our final simplified answer here. 1 over x times ln 10. So the derivative of log of x isn't just 1 over x. We wanted it to be, but it turns out it's 1 over x times the ln of 10. And therefore, the derivative of log of stuff is 1 over the stuff times ln of 10. The ln of 10 is just part of this derivative rule. And then the chain rule says times the derivative of the stuff. And again, that derivative of the stuff is up on top. So let's use our brand new formula to find the derivative of log x squared plus 1. So we'll write it here. Equals 1 over the stuff times ln of 10, always ln of 10 for the derivative of the common log, times the derivative of the stuff, 2x, x squared plus 1 just becomes 2x. Okay, number 3, we're going to prove that the derivative of inverse tan of x is 1 over 1 plus x squared, and we will do that by taking a derivative of both sides of that identity, which again we should believe to be true. Tan and arctan cancel each other. They disappear. So let's write that identity with a little bit of space in front. And they're equal now, so they will still be equal when I take a derivative of both sides. As usual, the right-hand side is easy, and the left-hand side is where the difficulty is. Okay, left-hand side is tan of some stuff. The derivative of tan of some stuff from a previous class is secant squared of that stuff, and then times the derivative of the stuff. And the stuff in this case is arctan of x. And I don't happen to know at this moment what the derivative of arctan of x is. Well, I guess we do, because in the demo I just told you what it was. But now we're proving it, so we got to pretend we don't know that the answer is going to be 1 over 1 plus x squared. So we're going to take this equation and we're going to figure out what the derivative of arctan x is by solving this equation for that derivative. So here we go. The derivative of arctan is, and then we're going to divide both sides by secant squared of arctan. So we go 1 over secant squared of arctan of x. Okay, so this is fine. I mean, it's a perfectly good derivative, but again, it is not the derivative that is commonly thought of across the mathematical community for arctan of x. We're going to come up with a prettier version of that. Again, we already know the answer is supposed to be 1 over 1 plus x squared, so let's get there from here. First thing, secant on the bottom is the same as a different trig function on the top. Secant on the bottom is the same as cosine on the top. So this is really the same as cosine squared of arctan of x. So it's just easier to get it in terms of cosine here. And so again, this is another perfectly good form for the derivative of arctan. It isn't one that I had memorized, but let's draw a right triangle. We're going to call this thing here theta. And when we take the tangent of both sides, we get tangent of theta is really just x, and that leads us to a right triangle. So here we go. Theta here. I know that tangent theta is supposed to equal opposite over adjacent. So if I want to force this x to look like a fraction, I need to put an over 1. So that allows me to label my right triangle. The opposite side of that theta is x. It's here. The adjacent side is 1. We can find the hypotenuse with Pythagorean theorem. Square root of x squared plus 1. Take your time on that. And then let's come back to this thing that's in black here. Equals cosine squared of, so what we called arctan of x is theta. So this is really just cosine squared of theta. And so what we're trying to do here is just write down what cosine squared of theta is, reading it off of our right triangle. So here we go. Cosine squared, all right, so cosine, we're going to put in the parentheses, and then we're going to square it. So we know cosine is adjacent over hypotenuse. So look at this right triangle and read the adjacent divided by the hypotenuse. So the adjacent side to the theta is 1, divided by the hypotenuse is square root of x squared plus 1. And then we're squaring, so that means we can square top and bottom of this fraction, and we get 1 over x squared plus 1, which is, of course, the same as what we were told the derivative rule would be, 1 over 1 plus x squared. Okay, if you haven't read this scenario yet, go ahead and pause the video and read, but we're going to go ahead and jump into part A. Express theta in terms of h, so we're going to write down a trig function for theta. So looking at the angle theta and the two sides that are labeled, h is the opposite side and 8 is the adjacent side. So which of our three main trig functions relates opposite to adjacent? It's the tangent. So tangent of theta is opposite over adjacent, h over 8. And then we're going to solve this thing for theta by taking the inverse tan of both sides. So theta equals inverse tan h over 8. In part B, we're finding the derivative of theta with respect to h. So that means find an equation that has theta equals and take its derivative, where h is your variable. And so that equation is this one here, underlined in orange. And so derivative of inverse tan of stuff is 1 over 1 plus the stuff squared. In this case, the stuff is h over 8. And then times the derivative of the stuff. The derivative of h over 8 does not require the quotient rule, although you will eventually get the right answer. If you use the quotient rule, I'd rather think of h over 8 as being 1/8 of h. And the derivative of 1/8 of h is just 1/8. Okay, so there's my derivative. And then C says, what are the units for d theta dh? So we know that the units are always the units for the top over the units for the bottom. Theta is measured, it's an angle, so it's got to be measured in radians, not degrees. And then h, what was h measured in? Meters. So the units for d theta dh are radians per meter. What does it measure? It measures the rate at which the angle is changing as h changes. Rate of change of the angle, theta, measured in radians per meter. As h changes, but I'll just say as the point. What was the label for the point? P2 moves up and down. So d theta dh just measures the rate at which, like if there's a person standing at that point by the angle theta, it's the rate at which that person's head is moving up and down. It's the rate that the angle is moving. So you look up and your angle gets bigger, and you look down and your angle gets smaller. I guess straight ahead would be the lowest you could get. And then part D says, what's the limit of d theta dh as h goes to infinity? All right, well, let's take a look. So we've got d theta dh up there in green. I'll copy it down here. Limit as h goes to infinity of 1 over 1 plus h over 8 squared times 1/8. Okay, so we are sending h to infinity. And when we send h to infinity, just this part goes to infinity. I mean, it's infinity divided by 8, and then it's squared. So that means that the whole denominator is infinity, because adding 1 doesn't change anything. And then 1 divided by something really large heads towards a very nice specific number. 1 divided by something really large heads to 0. Multiplying by 1/8 does not affect the 0. So this limit is 0. What does that mean? Okay, let's take a look. H is going to infinity in this picture. That means that the point is, this h is getting bigger and bigger and bigger, which means the point is going up the wall forever. And as the point goes up the wall, this person has to look higher. Maybe the point is up here and then higher, and the point is up there and then higher and then higher. And the question is, what happens if we send h to infinity? Well, this person can only look so high, right? They can only look up almost at a right angle. And if you imagine this point is like a mile up the wall or 2 miles up the wall, and it just keeps moving up the wall, like you're hardly going to move your head at all once it's really far up that wall. And so the rate at which your angle is changing is approaching 0. At some point, basically, your head is hardly moving at all. And so that's the d theta dh. So we'll say as the point P2 moves higher and higher, the angle theta changes by smaller and smaller amounts. And in the limit, it is basically not changing when all is said and done.